La última vez nos vimos en Río. Nos hemos visto en Río la última vez, creo.
Já chegaste, Pepe, então você sabe.
Good afternoon. I'd like to introduce the next speaker, Professor Patrick Popescu-Pampu, at the University of Lille.
Thank you very much. Es un gran placer estar aquí para celebrar a Pepe, que admiro mucho, que es un gran amigo, y pues voy a repetirlo esto al final de mi charla. Así que, como tengo que encajar muy bien en los tiempos, voy a empezar. And I pass to English, so I will speak about combinatorics of real analytic morphifications, which is a work done in collaboration with three friends: Evelia Garcia Barroso from Tenerife, Arnaud Baudin from Lille, and Miruna Ștefana Sorea from Sibiu in Romania. It's a work which will appear in Mathematische Nachrichten. So let us start from an image which for some of you may recall the birth of singularities of smooth functions, Whitney's 1955 paper, in which he classified the generic maps from real surfaces to real surfaces. You may see here a surface which projects here to this vertical plane, and you see here a cusp discriminant curve. Nearby, here there are loci of folds. So here the surface is folding, and at this point it acquires this cusp singularity. The same image appears in Thom's catastrophe theory, in which, in fact, here, if you imagine the same projection and you take some point in the xz plane, if you take its pre-image, it cuts in this region the green curve in 3 points, and those points are to be seen as critical points of some potentials. And Thom was studying a general functions with applications to all kinds of sciences. Here we have to look at this picture in a third way, which is related with Thom's viewpoint. We have to look at this as a family of functions which starts from this function here. You see it's a function of the variable y, and here x is a parameter of deformation. For x equals 0, you take this formula and you get the function y cube. And its graph is this one, which has an inflection point at the origin. And now if you augment x towards positive values, then the graph of the function here becomes this S shape. So you see that here also you can see this as a family of potentials. What do we have in this picture? We have also this blue curve, this red curve. You see one is smooth, the other not, which means that they are not isomorphic. But they are very important in all singularity theory, because one here is the critical locus of the projection of this surface to the vertical plane, and this is a critical image or discriminant curve. Or if you want, one is an apparent contour in the source, the blue one, which gets identified here with this orange curve on the surface, and its projection, which is the apparent contour in the target. So I speak about these two apparent contours. Now, from the next page on, they won't appear anymore till the very end. So this image is important, but now you can forget it, and I will ask you to remember it only at the end.
What is the parabola?
Sorry?
What is the blue parabola?
So here, as I say, we can look at this. In fact, this surface here can be seen as the graph of this function of two variables, x and y. And then now we can project to the plane of x and z. Means z will be the value of this function. So we get a map from a surface to a surface. And seen in this plane of x and y, the critical locus is a blue parabola.
Projection map?
Exactly. So if you look at the apparent contour in the source, it is this one. It is just identified. Here it is lifted to the surface. So you see, either you look at it on the graph or you look on the source of the graph.
I don't see the parabola in the picture. So that cut and the orange cut.
Simply, here in the picture, it looks like having a cusp, but this is because our viewpoint. It is as if we look at this smooth curve in the direction of its tangent at this point. So I should have moved my eye to look perpendicularly in this direction to see that here it is smooth on the surface. Sorry?
Over the parabola, the
Yeah,
expression becomes acute.
exactly.
So what's the definition of a parabola?
So here, it's so you see here the map from the plane xy to the plane xz is given by x and y cubed minus 3xy.
Just tell me the definition of the parabola. What's the definition?
This is what I said, the critical locus of this map, which sends
Map.
the map from the plane of xy to the plane of xz,
X equals y squared.
which sends xy in x and y cubed minus 3xy.
So it's the critical points of the map from the xy plane to where?
To the vertical plane of the variables x and z. Z being this expression.
So it's the critical points of F.
Exactly. So this is simply the general game of taking a function of two variables, leaving it in a curved surface, and now looking at this surface, in fact, as a family of curves, and we keep one axis, the parameter of deformation, and we project to the vertical plane obtained by taking that parameter and the vertical parameter. So this is a general yoga of critical local of apparent contour in the source and in the image. So here what is important is that if we think of this as a family of functions, you see that the initial one for the parameter x equals 0, which is y cubed, has a degenerate singularity here. It is not Morse, but the nearby ones are Morse functions. Here we have only two Morse critical points, and moreover, the corresponding critical values are distinct. So in this talk, by Morse function, I will mean this. First, singularities are Morse, and moreover, that the corresponding critical values are pairwise different. So let me write this. We will look at the simplest kinds of Morse functions, arbitrary manifolds, but on manifolds of dimension 1, and the simplest ones, which are the compact intervals. So a smooth function defined on a compact interval has critical points where its derivative vanishes, and we say that a critical point is non-degenerate if the a Morse critical point. We say that phi is Morse, which means here a global condition, if we have the following things. First, all the critical points are non-degenerate. Second, they lie in the interior of Y, so not at the two boundaries. And third, their corresponding critical values are pairwise distinct. These are exactly the conditions which ensure the stability of this. If now you deform slightly in the C infinity space such functions, you get functions of the same kind. And what we are interested in is the combinatorial type of such functions, which means we want to kill moduli, what could vary continuously. So in particular, we are not interested in the precise critical values, but in the qualitative position of the critical values. And this can be encoded in the following object, the bi-ordered critical graph.
Are you sure it's stable on the C1 perturbation?
C infinity, I said, because in It's possible that it is an error, because I need to go to the second derivative. So indeed, no, that's an error. In fact, you will see that I will work with analytic functions. So, what?
That's not true.
No, that written that way is not true. I agree. Yeah. So, now let us look at a typical graph of a Morse function. Here we have 4 critical points. Here we have the corresponding critical values. And now you see, because we are defined on an interval in R, which has a natural orientation, and the values are taking in another real line, which comes with its natural orientation, we can order them. But we have 2 orderings of them. So for instance, these 4 points get ordered by 1, 2, 3, 4. If we look on the source, that's why we call this the source order. And in the target, you see that the smallest one is P2. And then the next one is P4, then P1, then P3. So this is, in fact, the and we say that the combinatorial type of the Morse function is this bi-ordered critical graph. The critical graph is simply taking this set here on the graph with these 2 orders. So why is this combinatorics? Well, for me, combinatorics is a study of finite sets endowed with supplementary structures. So here you see a finite set endowed with supplementary structures. This combinatorial type encodes exactly the function up to changes of coordinates in the source and in the target, changes of coordinates which preserves the orientations. So you can say that this is a way to capture the combinatorial type of a Morse function. So now what we will look at is situations which generalize the example I gave you before. We start with a series in 2 variables with real coefficients. As we assume it vanishes at the origin. And here we think about x as a deformation variable. And the variable of the function is y. So for the parameter equal to 0, we assume that we start from a non-zero function. And now when we change the value of x, the function will change. And we will need also the vocabulary of a primitive of such a function, which is simply a series whose partial derivative with respect to y is a starting series. So you see there is this dissymmetry between x, which denotes the parameter of deformation, and the internal variable of the space, which is y. So we look at this situation as a family parameterized by x of functions of the variable y, and this primitive as an associated family of primitives. So why do we need this? We need 2 pages to explain why we play both with functions and primitives. First, let's say what it means that a series, big, great F of x of y, is a Morsification. Well, it is a Morsification if it admits a Morse rectangle. And the Morse rectangle is something like this. It's a product of some interval 0r in the axis of the deformation variable x and some neighborhood of the origin in the space of y. And what we want is that this series be convergent on this rectangle, which means that it will really define a smooth function on the whole rectangle. The initial series was defining only a formal object initially. Second, we want that on this interval, the initial function f0 here has only 0 as a critical point. There is no other critical point there. And third, that if we restrict it to any other vertical here in the rectangle, we get a Morse function. And if such a rectangle exists, then we say we have a Morsification. And in that situation, we can say, what is a combinatorial type of these Morse functions? And here we need the stability property, which ensures combinatorial type. And second, you see that here we have choices of the Morse rectangle, which means the choice of I and the choice of R. And in fact, all of them lead to the same combinatorial type. So this is what is written here, that the combinatorial type is a combinatorial type of a Morse function, fx0, defined on I with values in R. Each time we have a Morse rectangle. And why we needed to look at primitives is that the Morse function of a Morsification big F of y depends only on this partial derivative. So in fact, if you want to determine that combinatorial type, it depends only on the function small f. And the function small f is a function which defines exactly here this curve along which the critical points move. So in fact, each time you take a vertical segment, it cuts this blue curve in the critical locus. So here what you have an image of the movement of the critical locus, which was only one point here. And now when x augments, well, you see that it splits into several points. So the question becomes, if we give a series like this of two variables, first, so you give an expression, this is a starting object, determine whether its primitives are Morsifications. One is a Morsification if and only if all of them are Morsifications, and all of them then will have the same combinatorial. And if so, we want to determine this combinatorial type. So the question is to build a machine which transforms a series into a bi-ordered set. And that machine should first say, yes, there is a bi-ordered set there. It means I have a Morsification or not. So we will achieve this aim under a hypothesis. Function verifies the injectivity condition. And I won't state it now because I want to push you on a flow to that condition. So for the moment, we had no idea of how to do this, and we began to think, and I want to show you how we thought and how we arrived at that condition, and I hope to show you that that condition is very general, and you will see on the example. I will give generality. Sorry? Of course. This is very easy to build. If you put symmetry, you have a function, in fact, of x and y square, then you have equalities of values on the right and left of the variable y. So it's not a Morse function.
Because you have the same thing.
Exactly. But you see that you need some symmetry to destroy Morsification. In general, if you put parameters, what you will get is that in general, it will be a Morsification, but the injectivity condition is something subtler, but you will see that that something subtle is exactly of the nature of what led Newton to discover Newton polygons. It's exactly that. So in order to tackle the problem, remember that geometrically everything here is controlled by this curve. So it's a germ at the origin, and we know since Newton that studying germs of curves at the origin of the plane can be done using Newton-Puiseux series. So this is what we will do here, but here we are in a real situation. It means that we will need to deal with real Newton-Puiseux series. Not only, but partly. So let us introduce notations. In the sequel, K will be one of the fields R or C, and our notation for the algebra of convergent Newton-Puiseux series with coefficients in K will be this. K of x to the power 1 over the set of natural numbers, which denotes simply you take some convergent power series in the usual sense, and you replace the variable t by x to some power 1 over n. And these are Newton-Puiseux series, and the convergence comes from the convergence of G here. And now, if we start with a series f with real coefficients, then the Newton-Puiseux theorem, which tells that, so here, in order to understand this expression, we have to think in a modern way in two steps. First step is Weierstrass preparation theorem, which tells that f will be a unit times a polynomial in the variable y with coefficients which are series in x. And second one is what is called Newton-Puiseux theorem, which describes the algebraic closure of the field of series in one variables, which is exactly the field of Newton-Puiseux series. And here we have the corresponding factorization using the roots. And we see that, you see that here, exactly like for polynomials with real coefficients, we can say, well, some roots are reals, and the others come in pairs of complex conjugate ones. Here we do this for series. So we have first this part, which is a unit, which has real coefficients. Meaning that it is a unit means that it does not vanish at the origin. Then the psi i's are in fact the real roots of f. This calligraphic r means roots of f, and the index r means that they have real coefficients. Eta j bars are simply the pairs of complex conjugate Newton-Puiseux roots. And exactly like for polynomials, usual polynomials, we need to count the roots with multiplicities. We have to do the same here. Therefore, these are not sets, but multisets. So we have series, and we have to say with each element what is its multiplicity. And the same here for the set of complex roots. So now remember, we want to say that the primitives of these will be morphifications. So first of all, near each critical point here, we want it to be non-degenerate. This means that we want this real curve, blue curve here, to be reduced. And to be reduced means that, in fact, we do not have multiplicities in the real part. So we say that f is reduced to the right if this is a set. And we will always suppose multiplicities. What happens on the right is completely different to what happens on the left. Think about the initial fold projection. On the left, we would not have any critical points. On the right, we have two. So in order to speak about the corresponding combinatorial type, we need to say that the deformation variable x is either positive or negative. And here we have the convention that in the whole paper, it's always positive and small. So from now on, that f is reduced to the right, meaning that here each one comes with multiplicity 1. And this is the example which we use. You see, geometrically, we start with the usual cusp with equation y squared minus x cubed equals 0, which is shown, in fact, here. We take a second one in which we have put a coefficient here. We take c bigger than 1, which in fact enlarges the curve. So we get this second larger cusp. And then we have here a symmetric cusp in which we permuted y and x, which would be here. But because we are looking at x as a deformation parameter, it means that we have to think here of y as a function of x. And if you solve this equation as a function of x, you see that as Newton-Puiseux roots, we need how many of them? Degree 2 in y, 2 and 3, it makes 7. So we need to have 7 Newton-Puiseux roots. 5 of them are visible here. 4 come from these two cusps, and 1 of them comes from the unique real root cube is equal to x squared. 2 other ones here are complex conjugate. Rho is simply a cube's root of unity. And by a convention which goes back to the 19th century, we represent the corresponding real branches over this axis with dashed lines. So you see that this corresponds to eta, this series, and this to eta bar, which is this one. So here we have 5 real Newton-Puiseux roots, and 2 more which are not visible over the reals, but which have a role in the determination of the corresponding combinatorics. So finally, in the graph of the Morse function, we see something about the complex part, which is not visible in the direct topology, which is very interesting. So now let us think. What we are interested in is in being able to draw something like this. So in particular, we want to say for every pair of critical points on the graph, which is above the other. So this one could be above this one or below. So let's compare these two extreme ones. This could be below this one or above. So we want to make this decision for every pair, which is the biggest one. Which means that we the signs of the differences. Is there a problem? No, it's okay? So this was at the level of the primitive. So now if we go to the derivative, you see that the critical points correspond to the points where the derivative vanishes. So this difference appears as the difference here as the sum of these areas. This one plus this one plus this one plus this one. And these are alternatively positive and negative. So what we want to determine, what is the sign of this sum? But now this sum depends on the variable x. And it turns out that each of these elementary areas is again a Newton-Puiseux series, which is real, because you see we are speaking about a real object, which is visible. So what we are interested in is to look at successive sums of these areas and what happens when x becomes very small. And it turns out that the asymptotic sign will be in fact the sign of the leading coefficient. So our problem is to determine the signs of the leading coefficients of successive sums of these areas. So let me write down now. You see, I call this S, which is a surface. We call this the area series because we look at them as Newton-Puiseux series. And now we are interested in successive sums from some value Si to some value Sj minus 1. And this is simply a difference of critical values. Therefore, for x0 sufficiently small, the sign of the difference here is a sign of the initial coefficient of the sum. So the initial coefficient is corresponding exponents are sigma h. So now we make a sum of series. And if we want to look at the initial coefficient of the sum, simply we have first a minimization problem, which is that leading to Newton polygons. We are asking which exponents here realize a minimum. Each one we will have a value. We have to look which ones are minimal. We will have to make the sum here of the initial coefficients the minimum. So we do not have to look at successive sums of initial coefficients, only of some of them which minimize the exponents. And then we know the initial coefficient is this sum, provided that this last sum is non-zero. If it is 0, then we have to enter inside the series. And every time we want to determine the initial coefficient of a sum of series, it is not got simply from the initial coefficients of the series, the problem becomes much more difficult. It means that one has to go inside and it will depend on precise relations between the coefficients and it becomes complicated. So the first case in which we do not have complications is that in which all these sums are non-zero. And this is what we call the injectivity condition. It's that this non-vanishing relation holds for every pair ij with I less than j. So for each pair of critical values. And then you can ask, well, it's a non-vanishing condition. Why don't you call it non-vanishing? You call it injectivity. Because it's non-vanishing, will allow us to build injective functions, which will be the key of our problem. So keep in mind now that I have to show you some injective functions. Which ones? So let's advance. Come back to this problem. In order to determine that, we have to look now at a root tree, which we call the real contact tree of our series. Instruction in an example with true series. We do not have non-integer exponents here. We will use a notation which is when psi and eta are two Newton-Puiseux series, we say that psi is smaller than eta when the difference has an initial coefficient which is bigger than 0. Which means that, in fact, for x sufficiently small, we will have that psi of x is smaller than eta of x. So it describes asymptotically what happens when the parameter converges to the order. So imagine now that you have 4 Newton-Puiseux series. Here, in the example, there are 4 polynomials in x. And think, in fact, of them as series. And in order to see, we will look geometrically like this. We have a half line which starts from 0 and goes to infinity. Each time we have a term in our series, we look at the corresponding point with that value of the exponent. So this corresponds to the exponent 1. This corresponds to the exponent 3. So here we wrote nearby the corresponding monomial. So this shows, you see, that we have a monomial, which is x, and our x cube. Different. For x, you have only a special point in x, and for minus x is the same here. And now let us think that we do not know the series, that this line is like a scroll, and you begin to unscroll it, and you begin to read your series. And at the beginning, you see that all the series coincide. Before arriving at the exponent 1, you see that all our series are 0. So they are equal. And you unscroll, and you arrive at the first moment when you see a difference. It happens here for 1. So after having passing this moment, we see that these 2 are different. But these 3 are still the same. Because you see, you begin to see a difference between them only when you reach the exponent, which is 3. So this is what happens here. We encode everything in these 3. Till here, they are the same. So we glue these 4 segments into one segment. And here appears the difference between x and minus x. These 3 are still the same till x cubed. And here at x cubed, you see the difference between them. So they are split. So after having unscrolled at the exponent 3, now we see that we have 4 distinct series. And in this way, for any number of series, you construct, in fact, 3 in the plane. Why in the plane? Because we position here the ends or the leaves of the tree in the simply that the difference is 2x, and 2x is bigger than 0 for x small. So you see the order between the series in this order here. Okay? It can be done with series with complex coefficients, but there you cannot compare 2 series with complex coefficients. So simply we will get a rooted tree, but which will be abstract. The specificity of the real situation is that then there is a canonical embedding in the plane up to isotopy. That embedding tells you the order of the leaves. So the example, it leads to this tree here. You see that we will have, usually over the complex number, we say that here there is one cusp. But over the real, there is this half branch and this half branch, and finally we have 5 of them. The 2 cusps here lead in fact to series which bifurcate at the same point. So here we will have this order. Xi1, Xi2, Xi3, Xi4. You see that it's exactly the order of the half branches in the plane. And then Xi5 is above. And what you saw here, that they were tangent to different lines, in fact is much more special here because you see that this bifurcates before. And we have the precise values of the exponents where you have the bifurcation, which tell you much more. They tell you the contact between those series. And we don't have to forget the 2 other roots which do not have real coefficients. It means that this planar tree embeds in an abstract tree. So it's a tree which is partly planar and partly non-planar. So you see that out of this plane come these 2 other branches to 2 leaves which correspond to these complex conjugate ones. So this is what we have for any real situation like this. And now what we can do, this tree will help us think in the following way. First of all, when we have a real tree, we can say immediately, I have a poset. The poset is simply the tree in which we say that the smallest element is the root, and then if you have are uncomparable. So it's not a totally ordered set. And if you have 2 uncomparable points, so these 2 leaves N and L prime, you have their infimum, which is the greatest lower bound, which can simply be obtained topologically by joining the root to both of them and seeing where the 2 geodesics bifurcate. And they bifurcate here, and this is the infimum of L and L prime. This game of taking infima of points can be done on the complex tree. So also for the real one. The real one has a supplementary structure. The embedding in the plane, we have this total order on the side, which means that we can speak about successive leaves. And now, if you have successive leaves, you can play the game that you enter here and you arrive here at the infimum. So you get also successive branches getting out of the infimum. So you see that, in fact, this total order, which means a planar embedding, in a collection of total orders at each interior point. It means that this is smaller than this and this smaller than this smaller than this. And in particular, we can have a game now of taking the same abstract tree and re-embedding it differently in the plane by a game in which, say, for instance, here at this point, simply I change the order. Instead of saying that this is smaller than this, just permute the two. And then it means that this will be smaller than this one. And you can play this. And I tell you the nature of the answer to our question. The bi-ordered set, remember the bi-ordered set was a pair of total orders on the critical graph. But here the critical graph corresponds to the leaves of the tree. Because this tree corresponds to the derivatives, and we say this, the 0 points of the derivative, those give you the critical points. So a first order is this total order. How can you obtain a second total order? Simply by re-embedding the same abstract tree differently in the plane. How will we do this? By defining, in fact, at each point, getting out of the point. Those values of the function will give you the reordering of the edges. Reordering them, you re-embed the tree in the plane, and you get the second order. So the injectivity condition will be exactly this, which allows you to get a total order. Because assuming that you give values here 1, 2, and 2, then you don't know in which order to put these two. So only if you define injective functions at each internal point, you are able to re-embed the tree as a planar tree. So that's why this game can be performed only under this injective condition. Perform it. I told you that the first question was to determine between two roots which area series realize the minimum. So this depends on result, needs no hypothesis. This is completely general. We are looking at the initial exponent of an area series. So an area series is determined by two successive roots. That's why I spoke here of successive roots. Remember, from this picture here, you see you have here one area series corresponding to these two roots. Second series to Xi2 and Xi3. So that's why we need to look at successive roots. So here we look at them. We have an area series, and we ask what is the corresponding exponent. So the answer is this one. On our tree, we have the exponent function, giving the exponent to each point. Simply to each point of the tree, you associate the following function. Exponent plus a sum of exponents, which you will take the infimum of that point and all the roots, real and complex, taken with multiplicities. Here the multiplicities are crucial because this is the multiset. So you take this. And then the propositions, those areas vanish zero with that initial exponent, giving by this function, which in order to be understood, you see it needs the real tree. The real tree is fundamental in order to say how those area series tend to zero. This is what we call the integrated exponent function. And what allows us to see which realizes the minimum is the simple fact that this integrated exponent function is strictly increasing on the tree. This function is strictly increasing on the tree. We can determine the signs, and so the signs are determined, in fact, by the function in which, you see, we take for each successive pairs the corresponding initial coefficient. We make the sums of those initial coefficients, and the successive sums, by our injectivity condition, define an injective function, which we call a discrete integration map, because you see it's a sum, discrete sum of numbers corresponding to jumps from one point to the next one. So under this hypothesis, we get an integrated total order by re-embedding the tree and getting a new total order on the set of leaves, that which we denote here by the sign of smaller with the integral sign. That when our series is and satisfies the injection condition, then its primitive is a morphification and its combinatorial type represented by this bi-ordered set. You take real contact tree, you re-embed it using this discrete integration map, and that's how you get a bi-ordered set. And that's it. Since this, if you look at this theorem, you see that the answer depends on a re-embedding of the tree. And we saw that those planar trees come from real curves in the plane. So question, that tree corresponds also to some natural curve which is there. Let's look at the image. We come back to the initial image. In the initial image, I told you that we have two curves, which is the blue one, which is the apparent contour in the source. It is the blue one which gives us the initial tree. The answer is that under the injectivity condition, the re-embedded tree is a tree of the apparent contour in the target, of the discriminant curve. So theorem B tells that under the injectivity condition, the integrated contact tree is isomorphic with a real contact tree of the apparent contour in the target. In particular, we have a strong property in common between the two curves. Up to now, I did not have any property of the two apparent contours, a common one, is that their corresponding real contact trees are the same as abstract trees, but under the injectivity condition. So this, now what we did is completely computational, algorithmic, so it allows us to say that in this example, when we vary the parameter C, we get in fact 3 possible combinatorial types, and we compute exactly on which intervals we get them. Well, this is the end, and you may read what I want to say. Thank you very much.
Thank you. Question.
So, is there some takeaway if you just think of amorphifying something, the neighborhood in function space, you move around, and some property of this neighborhood that follows from your assumptions? I mean, you're trying to get
In the whole
feeling for the whole story.
Now, here, in fact, to say we were inspired, in fact, mainly by the work of Arnold on snakes for global polynomials in one variable, and second, by the work of Gis, which he explained in his book, A Singular Mathematical Promenade, in which he explained how when you have graphs of real functions in one variable, how they cross at some point, and that you have... The initial observation was explained to Gis by Kontsevich on a metro ticket, and then Gis unfolded that into a book. Okay, so a metro ticket transformed into a book. So we were, in fact, very much stimulated by this. And in the sense of what you say, is simply we say that a series can be seen as a germ of arc in the space of morphifications. And we say, if I give you a one-parameter family there, into which chamber of the space of morphification I enter? Because there is a big discriminant, and we enter in some chamber. How do I compute it? And here it's a way from the series to say where we enter. The part of the describing the combinatorics of the full space, this is more Arnold's work, when he looked at the snake story.
In this book, the operas play a role. But here it is an opera of three just playing the role.
Here, in what we do, not. And in fact, in that book, operas play mainly a role because Etienne Gis wanted to teach young people a lot of mathematics. But not in the first part. They play a role in the second part, in which he looked at germs of real plane curve singularities, and he encoded that combinatorics in a chord diagram, and he studied what chord diagrams are possible. And there he proved a beautiful theorem with Christopher Lloyd Simon. And there operas play a role in the recursive proof done by successive blow-ups, in the analysis of the resolution space and how different resolution spaces relate one with the other, because you can inject some space inside another one, and those are operatic operations. But here, no, we do not need to deal with operas. Here, the whole paper is completely elementary if you say define elementary by second year of university.
In Russia or Mexico?
Sorry?
In Russia or in Mexico?
How can you justify that why you relate your problem by taking a primitive, or starting small f and find big f by being a primitive according to a certain rule? Why
No, in fact, the initial problem was I take a series and I want to know if it is a morphification. And then we realized that in fact that depended only of its partial derivative with respect to y. And if we say that that is a basic function, all its primitives are or not at the same time a morphification, and all of them have the same combinatorial type. So this means that that combinatorial type is not an invariant of the morphification, but of the partial derivative. And sorry, because the first time you see that big F, small f, it's indeed difficult to follow. But it was this discovery that the initial problem is about big F. And in classical terms, you see the small f, you can say it defines the corresponding polar curve for people who studied polars of plane curve singularities. And classically, one tells, I start with a curve whose combinatorial type I know, and I want to determine the combinatorial type of the polar. And here is the converse. Here we start from the combinatorial type of the polar, and we ask what is the combinatorial type of the initial one. And it's not the combinatorial type of the curve we look at, but of the corresponding graph. So it is related. All of us here, if we found this problem nice, is that because all of us had drunk the milk of polars. So we are sensitive to that type of mathematics, and for this I have to thank Bernard Tessier, who was my advisor, and also Evelia Garcia Barroso. So since our thesis, we are accustomed to think in terms of apparent contours, target and in the source, and we are very happy to have been able to say something about both of them at the same time, because we feel this very concrete. When we look at objects, we have both of them here. We say something about looking at the world. So that's why I say this is my most elementary article, because it's about things which can be described here in three-dimensional space. No. We give examples where you have morphifications which are not like this. You can have morphification in which the type comes from deeper coefficients. You can have a lot of vanishing initially, and then you don't know exactly where you go. So.
Okay. More question? No? Thanks again.
Thank you.
We have returning 10 minutes.
voy a dejar rapar.
Aham. Se casa. Aham.
Now, I start again. I would like to introduce the last speaker of the day, Juan Nuno Ballesteros, professor at University of Valencia.
Thank you. So it's a great pleasure and a great honor to be here to celebrate the anniversary of my collaborator and my friend Pepe. So thanks to the organizer for the invitation. So this is a report on a joint work still in progress with Le and Seade and Pepe. And this is about generalization of the Legge-Royel formula. Okay? So the classical version of the formula, so the classical is that minor number of x plus minor number of y equal the dimension over C of the quotient O n plus k over f plus Jacobian of fg. So here x is an ICES which is given by k equations f1 fk is g of f, and y, so this is a ICES of dimension n in C n plus k, and y is obtained by adding one more equation. So fk and g, this is the set of zeros of f and g. So this is ICES again of dimension n minus 1 in the same space. Here the Milnor number is mu of x. This is the Milnor number of the ICES. This was defined by Ham. I think it's 71, maybe 71. So this was inspired by the Milnor number of a hypersurface with isolated singularity. So you take a Milnor fiber of the ICES, and then Milnor fiber has the homotopy type of, and the number of such pairs is this Milnor number. And for the other ICES. And this dimension, this can be interpreted geometrically as the Milnor number of the restriction G to X. So by definition, the sum of the Milnor numbers of G bar on X, where X belongs to the Milnor fiber of X. And this bar is an analytic extension. Analytic extension of G. So this Milnor is smooth, so this is the classical Milnor number, okay? So there are many versions of this formula and other formulas of the same type. So I will explain some of them. First, the Legge-Royel formula for space curves. In this case, we consider X a space curve. So curve means just that dimension is 1. And we take a function g on X, and we assume that this function is finite. So finite means the inverse image of 0 is 0. So the fibers are finite sets. Then the generalization formula plus degree of G minus 1 equal mu of G. So here, this is the number of a space curve which was defined by Buchweiss-Growell. This was So if the curve is smoothable, then you have a smoothing. The smoothing plays the role of the Milnor fiber, and then the number, has the homotopy type of a bouquet of 1 spheres, and the number of such spheres is this Milnor number. And this is the Milnor number of the function that was defined by Mond van Straten. In 2001. Then by definition, this is equal to the sum of the Milnor numbers of analytic extension of G at X, where X belongs to a smoothing of the curve. Okay? And the formula was obtained by myself and Tomasella in 2008. So observe that this term here can be seen when you have an ISIS, it can be seen as Milnor number. This is nothing but the Milnor number of the zero-dimensional ISIS. So this is, when you have ISIS, this formula is the same as this one, okay? Yeah, no, this is the smoothing. XS is the smoothing of X if it is smoothable. So when the curve is not smoothable, you have a definition which is more sophisticated. You have to use the dualizing module of Grothendieck, but for smoothable cases, it's easier to define, okay? Definition of this number. So, yeah, it is smoothable. So the general definition, you have to use the dualizing module of Grothendieck. Okay. Okay. So the next definition is LGF for isolated determinantal singularities also called IDS. So I gave a lecture 10 years ago, Pepe's anniversary, 60th anniversary, on this subject. But so I will not explain a lot because I have no time. But this is the formula is the following. You have X0 and IDS. You have G on X, a function with isolated critical point. Then you have a notion which is analogous to the Milnor number, but in this case, when it is isolated determinantal singularity, you have determinantal smoothing. So the determinantal smoothing is plays the role of the Milnor fiber, and then you can look at the topology of this determinantal smoothing, this Milnor fiber. What happens here is that this Milnor a bouquet of spheres, but instead of the number of spheres, you can look at what we call the vanishing Euler characteristic. This is -1, and the Euler characteristic of the smoothing -1. This is called the vanishing Euler characteristic. And then the formula is that mu of x0 plus mu of x, g minus 1 of 0 equal the Milnor number of g. And this Milnor number, by definition, is given by the sum of the Milnor number of g, of an analytic extension of g, on all points in the smoothing, the determinantal smoothing of x. So again, when you have an IC, which is a particular case of this, this formula gives the classical Lagrangian formula. Okay? And finally, there is one more for image Miller number. In that case, we take x0 equal the image of a germ f from Cn to Cm plus 1 with isolated instability. Then there is a notion of image Miller number. This was defined by David Mond in 91. So in this case, you take a deformation of the parametrization of the hypersurface, not of the equation, but of the map which defines X as the image. If you deform in the best possible way, then you have a bouquet of spheres, and this is the number of such spheres. Okay? This is called the image Miller number, and the Lagrangian formula is that this number plus this one, here H is a generic hyperplane, equal the Miller number of P restricted to X. So P is the equation of the hyperplane. And by definition, again, this is the sum of the Miller numbers of P restricted to XS.
What is the word after isolated?
Instability. This means that outside the origin, you have only stable singularities. Okay? For instance, if you might have something like this. From C2 to C3, so this is unstable because you can, by a small deformation, you can produce something like this. You have two winding umbrella. This is unstable and this is stable. But all other, outside the origin, all other singularities are stable. When you deform the parametrization, nothing changes. Okay? Okay, so what about general Lagrangian formula? So the main difficulty is to have a notion of Miller number for X, but also a notion of Miller number for G. So these numbers are, and you have to choose some specific class of varieties and some specific class of functions so that these two numbers make sense. So we consider X0 any complex analytic variety. And we take F, a mapping from X to CK. So if you want to associate a Miller number, you need a fibration. You need something which plays the role of the Miller fiber. So take a representative F from X to V. So this is an analytic set. So the closed analytic subset of some open subset of Cn. And this is also an open subset of Ck. And then this is analytic. Then we can always stratify this mapping. So we choose a stratification. We choose a stratification. we have S alpha, a stratification. This is a Whitney stratification. In X, also T beta, this is a Whitney stratification in V, and we assume that each S alpha, the image, is contained in some T beta, and more restriction, F from C S alpha to T beta, is a submersion. So till here, this is all possible. So if you want to define a fibration, then you have to remove here some discriminant. You have to remove the bad set here. So for the bad set, we define the discriminant. So discriminant is delta equal to the union of T beta closure such that the dimension of T beta is less than K. So this is closed analytic in CK, in V. Is analytic of dimension less than K. And now we remove this bad set. We consider the restriction F from F inverse of V minus delta into V minus delta. So we can assume this is an open, connected stratum. And then this is a submersion, and this is a submersion. Okay? What fails here? What fails here is that this mapping is not proper in general. This is not proper, but not proper. So we cannot use the first isotopy lemma. So now we make a definition which has appeared this morning in the lecture by Aurelio Menegon. More or less is the same definition. We say that F admits a Milnor left vibration MLF if for any delta and epsilon small enough, the restriction of F to the ball of radius epsilon, intersection with X, intersection with F, the open ball of radius delta minus the discriminant, into the radius, the ball of radius delta minus the discriminant. This is a submersion with the induced stratification. What happens is now this mapping is proper, but because this is the closed ball, this is compact, and this is the restriction of a proper mapping, so it is a proper mapping. Okay? Then, because you have stratification here on X, this is open here, no problem, you have to take just the intersection without open set, but this is a manifold with boundary. So the problem is the boundary here. The boundary has to be transverse to the stratification. Okay? Okay, so now this is proper. And then we have that it is a locally trivial fibration. And the fiber FF is equal to B epsilon intersection with X intersection with F minus U, where U is in the, okay? This is the fiber. Well, so this morning, I think Aurelio,
Then the fiber.
no, but this, no, sorry, nothing with this map is proper, then it's locally trivial fibration. We call, sorry, this definition. Yeah? Sorry. So this morning, Aurelio already proved that if you have Thom condition, then Thom condition implies a Milnor-Lee fibration. Lemma. In particular, there is a theorem by Lee in 76 that any function has Milnor-Lee fibration because it has Thom property, Thom condition, okay? And in this case, the discriminant is only the origin, okay? So the choice for the discriminant is only the origin in C. Okay? Thom condition. Thom condition, I think Aurelio this morning explained, but I will explain. If you have any sequence xn in a stratum S alpha, which converges to a point in S beta, then if the kernel of the differential of f in xn converges to a t, then the kernel of the differential of f at x is contained in T. This is the definition of Thom condition. Okay. Yes, it's a condition similar to the Whitney condition, but for mapping. This is for mapping. Yes, for map. Yeah. Okay. So strategy. We start with any function and then take a function, another function g, which is good enough such that the pair gf has Thom condition. In such case, we have a fiber. We have fibration, a Milnor fibration for this pair. Unfortunately, there are examples where you don't have this condition. Yeah, to have a well-defined Milnor number for Oil formula. To have Allegro Oil formula, we need fibration for one function, but also we have fibration for the pair. So we need some condition which gives fibration for this mapping, for this F, and some condition which gives fibration for this pair. Okay? So there is an example, also appeared this morning. the example is due to Le, but it appears published in a paper by Saban. We have F and G. We have mapping from C3 to C2. X, Y, Z goes to Y x squared minus Y squared Z. This does not admit. Milnor-Le fibration. And then, of course, no Thom condition. So we need to put some condition. This is F, G. We have to put some condition on G, so that we have this Thom condition. So our definition is the following. We say that G from X0 to C has strongly isolated singularity with respect to F if we have three conditions. The first one is that this set, which is defined as the C of phi minus F inverse of 0 closure, this is a curve. This is a curve. And here, phi is the pair GF, and C of phi is the critical set, the critical locus in the stratified sense. Okay? Second one, and this is called curve appear. The second is that this curve gamma intersected with the inverse image of 0 is only the origin. And then in particular is that the image phi of gamma is also a curve in C2. And this curve, using the terminology of René Thom, this is called Cerf's diagram. And finally, the most technical question is about limiting tangent hyperplanes. The third condition is that if we take any stratum S alpha in X of dimension at least 1, then nu S alpha bar F inverse image of 0 intersected with nu U G bar inverse image of 0 is the empty set, and these are the relative conormal bundles. Of this and of this. So this means in the limit you don't have fibers edge of F and of G bar. G bar is the extension. G bar is the analytic extension of G. Then the theorem is that a strongly isolated singularity implies Thom condition. And in particular, we have a Milnor left vibration for the pair. Okay. Okay. So another theorem is that this condition also implies that G admits a relative morphification. GT. So relative morphification means that for t distinct from 0, G sub t is a Morse function on the fiber of F. And finally, the main theorem which is general Lagrange formula, is that if G has a strongly isolated singularity with respect to F, then the Euler characteristic of the fiber of F minus the Euler characteristic of the fiber of the pair is equal to minus 1 to the power n times the sum of d delta times m delta alpha, times m alpha for all alpha. So here n is the dimension of the fiber. Delta alpha is the number of critical points of the morphification restricted to the stratum in the fiber, and m alpha, this is a coefficient which only depends on the stratum S alpha intersection with the fiber. Okay. So this, in particular, when you consider the case of ISIS, this gives a classical Lagrange formula. Yeah? Because we have these theorems, this fiber is well defined if G has a strongly isolated singularity. And also the relative morphification GT is well defined, again, when you have this condition. Okay? To finish, I will explain a particular case which is very nice. Assume that X is smooth, is Cn plus 1, and we take G and F from Cn plus 1 to C, such that G has a strongly isolated singularity with respect to F. But F can be any function. We don't have isolated singularity for F. Okay? Then the Euler characteristic of the fiber of F minus the Euler characteristic of the fiber of the pair is equal to minus 1 to the power n of the dimension over C of O n plus 1 mod out F plus the Jacobian of Fg with the saturation by F. This is the saturation ideal. Then, when F and the pair F both define I, we recover the classical Legge-Royal formula. In fact, in this case, what happens is that this saturation of the ideal, Jacobian ideal of Fg coincides with the Jacobian ideal itself. Okay? And I have time, I will put an example. We take f and g from C3 to C. In this case, of x, y, z is x, y, z. So this f defines triple point in C3, a surface of a triple point in C3. And g, x, y, z is x plus y plus z. It is not difficult to see that this g, it has strongly isolated singularity. So this has a strongly isolated singularity with respect to f. In this case, the fiber of f, this has the homotopy type of S1 times S1, so Euler characteristic is 0. The fiber of the pair, in this case, this is the Milnor fiber of the plane curve given by x, y, x plus y. So this has Milnor number equal to 4. This is D4. So Milnor number is 4, and then the Euler characteristic of the fiber is equal to -3. So the difference of the Euler characteristic is -3. And now we compute Jacobian ideal. The Jacobian ideal is the ideal generated by the two minors of the matrix of the Jacobian matrix, xy, xz, yz, and 1, 1, 1. This is a plane curve given by the D4 singularity.
What's the dimension?
The dimension? 2. This is a plane curve. No, because no, the fibers dimension 1. So yes, yes, dimension 1. Well, you can take compact or not. The Euler characteristic is the same.
Just no surface has all the characteristics.
Oh, this is a bucket of S1. So this F has the homotopy type of S1 times S1, S1. No, sorry. S1, 4.
There's no compact, so compact, the one is still.
No, you can take compact or not. It's the same. The Euler characteristic is the same. You can have the boundary if you want. The boundary doesn't matter for the Euler characteristic. Okay?
We're good, we're good.
Okay. And then saturation, in this case, is not difficult to see that gives the ideal which defines the diagonal in C3. So y, x equal y, sorry, x equal y equals z. And then the dimension over C, O3 quotient is x, y, z, and then y minus z and y minus x, but all this is equal to 3. So the formula is okay. Okay. Okay, I think I will finish here. Okay, thank you.
Question?
Have an analytic formula in the case where the domain is smooth. When you have an arbitrary stratified X, do you think there's a chance?
Yeah, that's a question, and we are, but for the moment, we don't have yet. But the idea is to find an algebraic formula in the stratified case. It's okay. It's a nice formula. But for a general case, we still have. I think I don't know if it is possible or not. Maybe it's possible, but for the moment, we don't have.
Do you think this problem can in some way be approached by characteristic classes, internal classes?
Yeah, maybe it's this is a different approach, but maybe it's possible. My feeling is that we should use more the relative conormal bundles. Maybe some algebraic invariant related to the relative conormal bundles will give this formula.
General theorem unifies all the initial theorem, also with the infinite number.
No, because here we are working only with one function here. So to generalize everything, we should need something like this. Fk from X to C. And now we take another function. This should be the most general version of the Legorel formula, but for the moment we have only k equal 1. This is the sum. The sum of all these terms is given by this number.
That formula you write actually comes from a stronger result, which
Yes. In fact, yes. We have. So this formula comes from a more general result that you can obtain the homeomorphism type of this in terms of this by attaching cells. So this is a more general. This is just a consequence of this more. But I have not much time, so I prefer to put this simplest version. But in fact, you can recover the homeomorphism type of the fiber in terms of this by attaching cells. Okay, so this is based on stratified Morse theory. So stratified Morse theory gives the homeomorphism type in terms of the cells that you have to attach, given by these two numbers. Okay.
Raimundo.
Sorry?
Raimundo.
The condition 1 and 2 seems very natural.
Yes.
But what to say about the condition 3? What's the geometric meaning?
Yeah, this is you have this condition because in the example by Le, where you don't have mean nor Le fibration, the condition 1 and 2 are okay because the example of Le, yes, Sabat. In such case, condition 1 and 2 are okay, but what fails is condition 3. Because if I remember well, in that case the polar curve is empty. In that case the polar curve is empty, I think. So condition 1 and 2 are okay.
More questions or comments? Thanks again.
Now we have a more gathering of them to do something.
Marco Antonio Gutiérrez Garduño está presente. Marco Antonio Gutiérrez Garduño. No, parece que no está. No está.